Welcome. We are ready to begin the webinar, and we thank you all for attending and joining us for the new focus of 3D Vision Measurement webinar brought to you by Mitutoyo America. I am Elizabeth Engler-Modick, editor of GIE Media's manufacturing group of magazines made up of Today's Medical Developments, Aerospace Manufacturing and Design, and Today's Motor Vehicles. Your presenter today is Michael Creaney, Vice President of Sales at Mitutoyo America. Mike will discuss the fast, flexible future of 3D vision inspection for the medical device industry, covering details about non-contact optical data collection methods to improve measurement capabilities, especially in situations where razor-sharp accuracy is of life-saving importance. Now, just a few notes and housekeeping before we get started. You will have an opportunity to ask Mike questions at any time during the presentation. However, we will hold off on answering the questions until the end of his presentation. Questions may be asked by typing them into the question box on the right-hand side of your screen, and we will do our best to get through as many questions as possible. Also, I wanted to mention that we will be hosting another webinar from Mitutoyo on Wednesday, August 15th at noon Eastern Standard Time, covering leading-edge quality measurement technologies for automotive manufacturing. Registration for this free webinar can be found at www.todaysmotorvehicles.com. So, without further delay, I am turning things over to Mike.
Good morning, everyone, and thank you for attending. My name is Mike Creaney. I'm the Vice President of Sales for Mitutoyo America Corporation. Today's webinar will certainly focus on some vision measurement capabilities, and we'll start right off with what this webinar is about. So we'll discuss some emerging developments of the three-dimensional vision measurement technologies. We'll look at some non-contact based measurement. As many of today's vision systems have many optional sensors, including tactile, laser, what we call chromatic sensor, and white light. These are all called multi-sensor systems, and what we'll review today is the traditional measurement perception of what a vision camera-based system is, some further development of non-contact sensors and optics, and some emerging methodologies to achieve 3D capability with your vision measurement machine. The outline will focus on the move from 2D to 3D, and one of the reasons why, of course, is more bang for your buck, as everybody wants to put every measurement task on one system. The two methods we will talk about today is a method called points from focus, and some applications specifically that we've run across in the medical industry, and a newer technology from Mitutoyo called Tunable acoustic gradient objectives. So that's a pretty big word, but we call it TAG, and it's TAG optics. And there are some really specific applications in the medical industry for that as well. So what is the traditional perception of vision measurement? So in our past, and we've all found that most people view vision measurement as a two-dimensional measurement. It's always been great for flat parts with high throughput, good edges. It's got great accuracy. But Z measurement has always been a weak link in the vision measurement world. With some of the newer technologies, it's moving beyond this two-dimensional world. And two of the main factors are really the increase of processing power and the continued development of image processing. So the horsepower that we have now is much greater than we had, and some of the optical designs are now starting to realm into the third dimension. You can see on the right here, there's a quick picture of some measurements done by optics, and that's pin set heights on a connector. So you can see the detail that's actually able to be provided with some vision systems. So the camera and optics certainly continue to evolve with all new designs, and it is really at a dizzying pace. If you stay ahead of cameras in general, there are new ones released every month. So the combination of these high speed, high resolution allow us as a manufacturer expand beyond the traditional measurement techniques that we were 2D based. And again, a lot of these have onboard processing power, and they eliminate the complex frame grabber software and the computing ability, so we can scan larger image and process millions of points. So they're changing the way we measure these optics and hardware. We get that more flexibility in a single platform. It's very desirable to most customers. And again, these hybrid machines provide a better cost of ownership and complete difficult 3D measurement tasks. The other part is our customers demand that 3D models and digital design. It's very common with most customers now. We have to do some contour analysis in both 2 and 3D, and that's pretty much a requirement on most workpieces. Many of today's vision metrology challenges are 3D related, as traditional designs do not have the ability to access all the features. This is a metal stamping image on the right side. It's very difficult to look at and measure with vision, but as you can see, the technique used here, we get a 3D map of these indents. The first principle we'll talk about is what's called points from focus. So what is points from focus? Some other people call it different things, extended depth of focus. It is an optical data collection method. So what that means is we add to the system with software and lenses. The hardware really doesn't change in the system, so it's pretty affordable from that point. So it is optical. All we have to do is select a part. We put the optics over it. We set the region of interest, and you can see the small little red area there. And then we move it in the z-axis, and we collect a series of images. With that, we build what's called an image stack. And that stack is then put together into a singular data field, and we create topography from that pixel data. So as you can see, these are the 5 scans. Z1 is on the bottom, and you can see everything is almost out of focus. The signal is very low. That means there's not a lot of data in focus. And as we cycle through these, Z2 is a little bit better, and you can see some more signal, and then slightly more focus, and also the contrast signal increases. As we go to the third stack, we see a much higher area in focus, and we also see a high contrast signal. We go beyond that, and we actually start with the top. This is a thread application, and the center region is in focus, and the signal intensity is very high in the middle, as you can see the sharpness of the image relating to the contrast. And lastly, it's defocused beyond it, and it's out of focus. So the contrast signal there is very low as well. So we take the sample part. In this case, it's a bone screw, which is a pretty complex set of geometry in general. We actually do the field of view, the result of the camera objective and magnification. We generate topography. A typical example, this process takes about 6 seconds, and you're probably looking at 350,000 points in that point cloud. So we get that image stack, and we take that, and then a lot of people want to do a 2D analysis. In this case, we actually cut the workpiece with a region of interest, and then it actually puts it out to a form-related piece of software. So we'll do contour and profile analysis of this. So this is a 2D method, but we also have a 3D method as well. So here are some application examples. A lot of these pertain to the medical world. So medical devices have lots of components, including electronics now. But you'll see on the left side, we talk about a bone screw. There's a ball grid array, which is a chip component. The third one is a parting line. So this is injection molding, which is pretty prevalent in prototype and also some medical devices. Some circuit boards and flex circuits. One of the hardest things to measure is called a bone plate, which is a spinal implant that's very curved. There are no flat piece part of that. And then the last one is an example of a knurled pattern or surface finish. So those are the sample parts. There's an idea of the field of view. the topography, the sectional of the part, and then at the bottom, what would be sectional analysis of that particular part. So in this case, this is a short video. It will show you a measurement of a sphere. So this is optical scanning. We tell it where to go. No datum is required to do this measurement. You just put the part underneath it and hit a button. So we're defocusing. We're going below the part. We're pulling the z-axis up. We're going to the high point and the low point, and this is setting the stacking of where we want it to run. We can adjust the lights. It does have automatic light adjustment as well. So it is a single field of view in this case, and we're going to take this measurement, and then it will actually build the 3D topography of this, okay? So again, down the bottom here, that's 278,000 points in about 4 seconds. When you add lighting to it, you actually does take a little bit longer. You do have some tools here where you can actually make the pixels interpolate a little bit better and fill in some of the noise ratio that you get. This is a sphere. It's a piece of solder, so it does have a high spot on the top. So let's talk about the difference between conventional vision measurement versus points from focus. So on the left-hand side, typically we go to the edge of the part, we focus in, we get an edge, we ask for distance. So in this case, it's showing 2 edge detections on the top. They're actually here. I'm not sure if you can see my mouse, but right across here, those would be traditional edge detection. The other 2 are actually surface measurements. So edge detection would actually do width or distance across, and then the 2 top focus would be height, so Z height from the top. With a points from focus, that single field of view that we would have used 4 tools for is achieved, and it will give us a 3-dimensional rendering, which in this case, all of this stuff we can do. So in a traditional conventional measurement, the radius in the ZX axis here is very hard to do with vision. You just can't see it. But when you do it with PFF, we can actually calculate the radius, or the corner radius is on the top. And those are really important to customers and very hard to do. There are many contact methods for this, but they do damage the part. So with an optical methodology, we don't damage the part, and we actually can measure down to, a couple of thousandths radius or better, depending on magnification. So here's some examples that I wanted to put out there. Always, what's my part look like and what do I do? So this is a seal. And on this particular application, you can see where the exploded view is. These are really hard edges to see, okay? So they're very shiny. They're not very sharp, so the camera gets confused as one edge lies over the other. But the real challenge is, number one, was poor edge detection, and of course, it's highly reflective in some areas. And the customer requirement in this case was the measurement of a radius in the ZX axis, so from left to right across, kind of on the equator. But it had this unusual multi-blended radius, and it had all kinds of curves in it, and there were like 5 different dimensions. And tactile measurement, meaning measurement by a touch probe, is not really possible, as these radiuses are quite small, 30 thousandths in nature. But you can see on the right side, there's a scan of the PFF extracted data, and it's very clean and very clear, and we can evaluate all the radiuses. So a really good application. The second one is a piece of plastic, and it's actually called a parting line. So many injection molded workpieces have mismatch, and the mismatch is typically called a parting line. So on the upper left-hand side, we see this parting line. We stitched together a bunch of images to show you the full part. Underneath it is what we can do with vision, and you can see we're limited to what we know and what we can see, and we would measure distance. But with PFF, we actually extract this same field of view as on the left, and we now get surface topography, even though it is a cylindrical part, okay? So there's a cylinder, and that's the break point. What this allows us to do is actually evaluate the contour extraction and find out what that parting line is. So we can do an image match or some kind of flashing, but it's very good for examining the plastic injection molded parts, okay, which medical has a lot. The next is an example of a plunger. So again, a really sometimes difficult application because of its cylindrical design. And there are some very unique dimensions on this particular one. The region of interest actually is on the top and on the bottom. So again, we extract this three-dimensional set of data, and then we bring it into a 2D evaluation. And if you see the bottom ISO view and then the evaluation, you can see this particular contour is actually offset. So real hard to measure. It's not flat. It's on a cylinder. It's got probably the three hardest things to see, to evaluate, but quite easy. Again, we're talking about 4 or 5 seconds to do this evaluation. But beyond a single field of view, which is what everybody wants, we can actually stitch together up to 1,500 fields of view, okay? Lots of data. Here's an example of a gear. It's a crown gear. And we can actually tell it start and stop points. It will then evaluate all the fields of view. It will do individualized one, which you see the first field of view on the side here. And then in the end, we actually stitch together all this stuff. So here's a 15 millimeter, basically, diameter part. It took about 2.5 minutes to do this. Now, in this case, we're probably looking at 20 megabytes of data on this data set. So each field of view is 300 to 600,000 points. Okay, so we do offer pretty high-powered PCs when we get to this level. Again, this is a 3D evaluation. And now we'll talk a little bit about what are those advantages. So it's low cost. For us, we retrofit it to our current platform. It's pretty high throughput depending on how much region of interest you have to do. Again, we can integrate it into our existing system. We call it medium vertical resolution. And we call it lower accuracy, believe it or not, but it's really about 2 microns accuracy. There's no coordinate system required. And again, we can do 2 or 3D profile evaluation to a CAD model. So this is a stamping with a bump on it, which is metal. And it has a unique contour as well. And you can see it's very easy to disseminate all the radiuses and angles and intersection and height distances. It has some limitations. So it's sensitive to the material surface. If the part becomes too mirrored or too shiny, we have a reflecting issue. We do have some abilities to circumvent that by lighting, but clear parts are difficult to do. And we call it low accuracy. Many others might not, but it's 2 microns. So what are the applications that we see in the medical markets? And I'm going to go, segments is on the left, applications is on the right. So we have a wide variety of things that we have done. Orthopedics, we've done joints, inserts, bone screws. We've done implants for defibrillators, stents, dental, real good application with implants, abutments, and crowns, really small stuff. Needles and catheters. So lots of detail on the tips of needles in some case. You'll see a little bit more about that later. But also the moldings, the tubing, the contours. Certainly medical has evolved into lots of electronics. So there's flex circuits and circuit boards and pins and those things. Plastic injection molding, again, we talked about parting lines, contours, and radiuses, all hard to really evaluate. And 3D printed, so we see a movement in a lot of medical devices that actually have 3D printed materials. It's getting cost effective. There's also applications where the one-off 3D printing is much more affordable than machining something, okay? Particularly in spinal implants. Threads and knurls, everything has threads, it seems like. And surface conditions, we can see the bumps, some V-grooves, steps, and chamfers. So those are some segments and applications relative to that. The next topic we're going to talk about is tunable acoustic gradient objectives. And that's a lot of words, okay? We call it tag optics, okay? The history of this company, Mitutoyo purchased them about 2 years ago. It was a startup at Princeton University, and we found the technology to be very useful. And it is an emerging technology for us. And it kind of crosses over from the traditional methodology of having it on a platform. It's more built to order. So a lot of people can use the technology in a way beyond that. So standard lenses use solid glass lenses, okay? And if we take a look at the human eye, it can reshape its lens. So we have the ability to change what's called the wavefront, okay? That means that we pulse through with ultrasonics and we get on the top here a bunch of wavefronts. So it looks very similar to PFF in its general application. So there are some examples. There are mechanical tunable lenses, there's optical, there's thermal, and electrical. This is different as it is acoustic. So that's the big difference with this lens. So what is this objective to? Okay. It uses an objective lens with liquid inside of it. And then it uses sound waves to shape that liquid. It uses sound to shape light. Okay, it can be done at very high speeds. You'll see some of the examples. It's milliseconds or less than milliseconds. It provides the ability to capture image information at various depths. So when we talked about PFF, it was very much a mechanical methodology. We moved the stage in Z up and down. This one moves light and acoustics through the part. So there are no moving parts on this particular application, where the other one is actually subject to the accuracy of how good we can make a Z-axis and its methodologies. It provides a large extended depth of field. So one of the challenges with vision and vision measurement is we always seem to be limited by the physics of the lens itself. That means that we only get a certain depth of focus, and the tag lens augments the methodology to do this. So it's a high frequency. It's 70 kilohertz to over 1,000 kilohertz, and it allows for volumetric imaging. So one idea is to take this and we look at imaging. Sorry about that. The other image is actually showing you three-dimensional data. Sorry about that. Close it. So here's a standard system. We have a camera and a sensor, and then we have a depth of focus here. We also can see beyond that, but we're actually moving the lens array to get what we need. Those are called individual focus planes. Now we put a tag lens on it, as we said, no moving parts, and you're able to extend the focus of a lens by a longer margin. These are three individual lenses. This is one lens actually being set out by tag. So all that info is instantaneously available to you. So here's a traditional system. The lens is a 35. This is just a camera with a tag lens on it. The depth of focus is a very small 8 millimeters in that sense. With a tag lens, our depth of focus actually expands to 800 millimeters with the same setup with the tag lens on it. So we also have the ability to put synchronized light on this, and that actually extends us to even higher intensity levels across the entire image set. So here's some examples of timed light pulse. So in the foreground, we see a picture of a euro. It's a 20-cent euro. The camera is an Edmund Optics 35 mm with f5.6. The native depth of focus is 44 millimeters, okay? And then we actually take this image as one image, and then we have another image in the background, which is a euro banknote. So you can see the first image, and if we go back here, sorry, you can see down the bottom, here's where our first image is. And then there's where our second image is. And then we pulse the lights so that it lights up these images, and we enable the tag lens, and you can see now we actually can see both images at once. So looking at the 3D capabilities, this is something that a lot of people want to use on their observation systems in general. And tag lens actually can be tuned to multiple planes. So it's a 12.5 times increased depth of focus. Some images that relate to the microscopy world and actually biology world, there's some cell count information going on here. So this actually can multi-level stack an image and see cells and capillary information go across. So I'll run a few of these, and you can see it's doing a depth. There's kind of a look at how deep the box is. And as we push material through the observation system, we're now able to see three-dimensional depth of the features. And the last one is even a little bit more interesting, as it has fluorescent calcium imaging. So the tag optics is really good for biological measurement on microscopes. So let me make sure I'm in order here. So here's another methodology based on tag. This is called an inspector. This is a product that Mitutoyo will release. We have some already, but we will be showing this one at IMTS for those who come. And then here is a picture of a needle. So the native depth of focus is 15 micron, but we took a high-speed camera. We put a 5x Mitutoyo objective on it, and we're able to image this with multiple Z stacks. Similar to PFF, but done with acoustics. And on the bottom left-hand side, you can see the detail of this needle was quite complex with its planes and its angles and its depth of focus. We can rebuild that imagery, and we can measure things such as bevel angles of all types, rotational angles, and the tip angle. So for those who may know a lot about needles, they're a lot more complex geometry than meets the eye. And a normal methodology may be multi-focus to try to do this. So tunable acoustic gradient objective advantages. So in this case, they're good for volumetric analysis, as we saw with the biology methods. A very large extended depth of focus. It's extremely high speed. There are no moving parts. It does provide positioning feedback, and there's no real need to focus or scan in the Z-axis, so no hardware controls. It is a simple integration, and we don't have to change the physical optics. Two limitations right now we see are camera speed. So with the advent of new camera systems, we now have a limitation on this based on how fast the frames can be collected. So some cameras we now actually have 2,400 frames per second. We can divide those into segments, but we need about 8 frames per second to hold an image. So it's always difficult. The faster the camera speed and the shutter speed, the better off we are. So there is some limitation with cameras. On the right side, you see a traditional system with a standard 10x lens, and on the left side, and on the right side, you can see the same method with tag enabled is actually 450 micron depth of focus. The other is intensity of illumination. So when you're doing multi-stacked imaging, illumination gets a little bit tricky, and especially if you're going a large depth of focus, you have to have light pulses. So you have to understand lighting in a pretty good way to implement this. So a couple of comparisons. We look at PFF. We have points from focus. That is a hardware-based contrast method. The Z-axis resolution is 50 to 100 nanometers. The contrast is the accuracy is we call low. The throughput is quite high. And again, threads and circuits and a lot of those other things that we saw before. And then we have the tag, which is extended depth of focus. Z-axis is about 2 to 3 microns. It is actually lens dependent. And then we have what we call a middle accuracy, but the throughput is ultra high. So we've seen applications in life science and packaging, imaging, security, QR codes, all kinds of different methodologies. And I probably went a little faster than I usually would, but we certainly can be open for questions at this time, and that will give us a little bit of time, and we'll get back to as many questions as we can. Okay.
Thank you, everyone, for the attention. And like Mike said, we are open to questions now. You can type those into the right, and we will work through them. We do have our first question that came through, and Mike, it is, how does this system work with CAD?
So there are 2 methodologies. With primarily, we'll talk about points from focus. So in the case of points from focus, we have 2 ways to work with CAD. One is we use a 2D slice method. You saw a lot of examples of that, and I can actually go back to a couple if you want me to. So that is a 2-dimensional profile. We take the image stack from PFF and we export it to a CAD-based system. So we would load a 2-dimensional CAD file, DXF, IGES, whatever, and we would then actually profile it against that measurement. The other one is 3D. So we can also extract multi-fields of view and take that point cloud and put it into 3D and look at 3D profile analysis as well. So it works in 2 ways, 2D or 3D. Does that answer the question?
Well, they haven't come back with a second question on that yet, so I think that's great, Mike. We do have a new question, and how does it work with the 3D models?
So in the case of that, it's probably an add-on to the first question a little bit. So Mitutoyo has a wide range of of analysis software. So with a 3D model, we would align the part with the model based on the vision measure machine, and then we would scan the region of interest that we want. We would put it up against the 3-dimensional array, best fit it, and then do a heat map on where it would be out of tolerance.
Great. And now we have another question. Mike, for tag, does Mitutoyo offer a device akin to a handheld unit for use by an operator who needs to get to a tight location?
So right now, our inspector is based on a stand, primarily a height stand methodology right now. Handheld, no, not at this time. The actual piece of equipment's a little too large for that right now. It's not miniaturized in nature. It's on par with a measuring microscope, but it does come on a stand. But we have integrated into system, but not handheld at this time.
Okay, now we have a question from Lewis. Can it dump into SolidWorks?
Yes, our point data on both PFF and the imaging can send XYZ data right into SolidWorks.
Okay, and now Stephen has asked us a question. I'm assuming with 3D compatibility, would FEMA be feasible on the model integrated?
So he's asking about FEMA analysis?
Yes, and if it would be feasible on the model integrated, he says.
I would expect it would be feasible, yes. That would be a reverse engineering technique, if I answered that correctly.
Okay, and then we have another question. How does this apply in the measurement workplace? And how does this integrate into general metrology?
So what we're finding more and more, as mentioned, is a lot of people actually need 3D profile or 2D profile. So the process is typically we set up a part, we put it on a vision machine. We can actually write a program to measure general features in the 2D range and do our datum alignment structure. And then when we wanted to get more informational stuff, we could actually then, we just add to the program to do the scans of PFF primarily, and then we can program it to dump it into a profile analysis, and it'll print out at the end. So pretty easily adaptable for a turnkey situation. It always is application specific a little bit, but certainly able to put it into a part program that measures dimensional measurements with a vision machine or a touch probe with it, and then PFF can be added right on as a part of the process.
Terrific, thank you. Do we have any more questions out there? Well, Mike, that appears to be the last question. So for everyone in attendance today, I would like to thank you for joining Mike and I for today's webinar from Mitutoyo. This webinar will be posted on Today's Medical Developments website in a few days for any on-demand replays or sharing that you would like to do. And just as another reminder, that Mitutoyo will be presenting the form measurement of automotive components high precision at production speed webinar on Wednesday, August 15th at noon Eastern Standard Time, and more information is available about this at www.todaysmotorvehicles.com. So thank you, Mike, for a great presentation, and we appreciate everyone's time.
Great, thanks all. And you certainly can contact me. My contact information is on the thing. If you have some other questions or more detail, don't hesitate to reach out to us.